Hello. Well, I've actually just finished my PhD, so demob happy at the moment, but thank you. I looked at could we detect cyber attacks on something called the Automotive Controller Area Network. Now, I'll explain what that's all about in a minute. But cars are becoming more and more reliant on data and information. They are sharing that information, both within the components within the car, but also to outside sources. So some of you have probably got cars at the moment where you've connected something in the car that connects with your insurance company or with the AA or RAC. And as cars become more autonomous and more connected, their use of information and data is increasing, and their need to share that information is increasing. Now, cars actually contain a few different types of network within them. But one crucial network is this thing called the controller area network. And on that reside the components that are crucial to the safety and the performance of the car. So things like the braking systems, the steering systems, and the engine performance systems. All these contain components that feed information and data onto this controller area network or take data off it. And it's been shown, unfortunately, that it is possible to hack in to the car and hack into the controller area network. There have been a few attacks publicised. Now, these have tended to be performed by researchers and academics like myself. But for example, one quite well publicised attack is shown here, and you can see this on YouTube if you search for it. These two researchers, Valasek and Miller, were able to remotely hack in to a Jeep Cherokee. So they were sat in an office somewhere. In the video, there's somebody driving who knew they were going to be hacked, but didn't know what was going to happen to the car. And Valasek and Miller are actually, because they've got a laptop that's connected to the internet, the car is also connected via cellular networks and other things to the internet. They were actually able to hack into the car while it was driving, and they started off doing things like altering the display on the dashboard. And then they concluded by actually sort of taking control of the engine, stuff like this. So they could do quite malicious things potentially. And the potential is there for hacking into cars, whether that's for terrorism, for holding fleets of vehicles to ransom in some way, or just the opportunist hacker. So what I've been looking at are ways that we can actually detect if this controller area network is being hacked. Because those attacks tend to occur by people injecting packets of information, of phony information into the controller area network, or causing those packets of information to stop being broadcast. So I've been looking at ways to actually detect this, and can we get systems that we can actually put in place in the car to detect these things happening. Now, it's actually not as easy as it sounds, and I'll explain that in a minute. But really, the research questions that I've had, therefore, I've been looking at are, can we actually determine, are there any characteristics that we can monitor within the car in order to detect attacks that might be taking place? And if there are things that we can monitor, what methods can we use to actually monitor the network? To actually decide if an attack is taking place. But we need to test any method that we're using. So I've been looking at the ways that we can test these and evaluate them as well. Now, I mentioned that this isn't easy to do. It's quite easy to capture information that is flowing in this controller area network. I can take my car, I can plug something into it, and I can actually record the data as it's being broadcast. As each component is broadcasting its packets of data onto this network, I can read it off. And here's an example extract of each of these rows represents a packet that's been broadcast. And there are about 1,000 packets or more every second that are broadcast onto this CAN network. So it's quite a high volume of data. as I say, I can read it, but what I don't know is what the data means. I know its structure. I know that there are IDs here for each packet, and that those IDs represent one of the components or are issued by one of the components that's broadcast. But I don't know what those IDs refer to. I don't know which component has broadcast these. I don't know what the data actually means. I know that there are going to be between 1 and 8 fields in each packet of data. But I don't know what it means. All that information and things like how regularly, how frequently the packets are broadcast, all that is a closely guarded secret from the automotive manufacturers. They don't reveal it. And even if they did, it differs according to the make and model of car, even the configuration of the car. So if we want to try and get things that might use the knowledge, that sort of knowledge in order to detect anomalies in this data, that's going to be very difficult. For example, one of the early proposals was that we could actually look at each packet that's broadcast, look at its ID, which gives us an indication of where it might have been broadcast from, and then look at the next packet that's broadcast and see if there's a pattern. So if we get this packet broadcast, that's from a certain component on this CAN network, and the next packet that's broadcast would be maybe another component that's been interested in this particular packet, has read it, and has broadcast its own data in reciprocation. And some people have proposed that this could be a way of detecting. So if we know the patterns of data that are broadcast, maybe we could look for anomalies in these patterns. But I did some early work where I just took a few cars and looked at the sequence of packets that are broadcast, and really, I won't go through this in detail, but it's just shown each packet, type of packet, each packet ID, how many different packets, how many different packet IDs could follow it. And frankly, it's almost, for some of them, it's almost could be any one of the packets could follow. So really, we can't just take one packet broadcast and say, therefore we're expecting this particular broadcast packet next. So we need, and in fact, we find that all these sort of knowledge-based approaches to detecting anomalies in the broadcasting of this data that rely on us really having a good knowledge of how many packets are broadcast, what they are and all that, it just doesn't work for the reasons I've said about the companies keeping all this information secret. So I've looked at other ways of detecting, particular ways called one-class classification methods. Now, these are ways that don't make really any assumptions about the data that we're that we're interested in. They try and learn about the data themselves. They try and learn the patterns in the data. So we don't necessarily need to know what their data means, but we get systems that will look for patterns in the data. So here, for example, is one of the methods that I looked at. I won't go through all the methods, there's quite a few, but here's one of the methods. This was something called a compound classifier. And basically, the blue dots here represent actual data that has been broadcast, the actual packet data that's been broadcast for 3 of the fields broadcast. And all I've done is plotted them against one another, done a sort of correlation. And you can see there's a sort of pattern to these dots. And because we know this is from a car that hasn't been hacked, perhaps we could do something like, if we can, whoops, let me go back again, sorry. If we can learn this pattern, sorry, technology, God. If we can learn the patterns of this broadcast, if there's another packet broadcast, a new packet broadcast, can we actually say, well, if it's close to one of these existing strands or the existing pattern of blue dots here, if it's close enough to that, it's normal. If it's far enough away, it's abnormal. Now that brings all sorts of questions about how close, how far away, all these sorts of things. And also it'll take time. It takes a lot of resources. So if each time we have to store all of these patterns there, all of these dots, coordinates, as it were, and then we have to do a nearest neighbour type search for any new broadcast, so we find out how close it is to these, and that all takes time. So something like this compound classifier, it learns. We feed all these blue dot data into it, and then it'll grow these hyperspheres, these spheres, these orange blobs, to try and encapsulate the data surface. And then any new data that's broadcast, all we need to do then is say, does that new broadcast data fall within one of these spheres, one of the orange spheres there? If it does, we'll call it normal. If it doesn't, let's flag it as an anomaly. So we can do it. It's a much more sort of rapid way of doing our sort of detection. So that's an example of sort of one of the methods that I've looked at. I've looked at quite a few others like that and analysed them and suggested which ones would give sort of the best results in terms of false positives, false negatives, etc. So I'm not going to go through all those now, but throughout this PhD I managed to get some sort of impact stuff done, I think. Managed to get a few papers published from it, 4 papers, ignore the bottom one, but 4 papers published so far, and got another one submitted as well, which we're waiting to hear on. Now, a lot of these were to sort of automotive conferences and engineering conferences, but I was quite pleased that we also managed to get a paper published in a conference in Kyoto in Japan and presented there, which was more to sort of machine learning conference. And I thought that was quite interesting to go and present our work there and see other stuff there. Managed to achieve quite a bit in that, for example, taking the automated discovery and parsing of the data. I mentioned before that we don't really know what the data means in the car. We don't know its structure, so I was able to parse all that and find methods to parse it. Able to simulate the type of attacks that we've got at a generic level so that we can take those simulations and actually use those to test our systems. Looked at anomaly methods as well, statistical methods for detecting if there were anomalies in the timing of the packets, and also methods for detecting if there are anomalies in the payload, because found that there are some attacks that could potentially happen that won't affect the timing, but will affect the payload. So we looked at all that and managed to propose methods and managed to test these across data from different car journeys and under different situations, all this sort of thing. So I thought that was quite good. Yeah. All right, but there are a few contributions as well that managed to get out of it, but thank you.
Thank you very much.
Yeah.